beginnings of the day. In this session, we will concentrate on basics of the root locus. Now first, if we consider the introduction part, now let us consider a closed loop system like this. So in this forward path is having two cascade connected blocks K and G dash of S, where K is the system gain, which is not given, which is a variable. G of S is the system parameters, G dash of S, and H of S is the feedback element. Now, in the previous session, we have studied analyzing the stability. So, to find out the stability of the system depends on closed loop poles. So, closed loop poles are obtained by characteristic equation. So, now for this particular system, forward path transfer function G of S is equal to K into G dash of S, because these two blocks are series connected blocks. So the characteristic equation of the system becomes 1 plus K G dash of S H of S equal to 0. Now in this particular characteristic equation, we cannot find the location of the closed loop poles. So stability depends on the closed loop poles. And if the closed loop poles are in the left half of the S-plane, the system is stable. If it is on the right half of S-plane, then the system is unstable. And if it is on the imaginary axis, it is a marginally stable. Now in this particular characteristic equation, until and unless the value of K is unknown, we cannot find the closed loop poles. So the value of the K varies. If the K, if we assign a 0, one set of closed loop poles, K equal to 1, K equal to 2. So it depends on the value of the K, this closed loop poles will vary. Hence the system stability cannot be determined. Or up to what value of the K the system is stable, beyond what value system is unstable. These are the things which we cannot analyze using Routh-Hurwitz criteria. So this is the one of the drawback of the Routh-Hurwitz criteria. Even from the Routh-Hurwitz criteria, we cannot find the location of the poles which causes the system unstable. Or from the Routh-Hurwitz criteria, we cannot locate the poles which are on the right side of the S-plane. So we will go with the root locus analysis. Stability using root locus. So before that, we should know what is the root locus and how to construct the root locus, then analyzing the stability. So first we'll see what is the root locus. Root locus is the locus of the variation of closed loop poles as K varies from 0 to infinity. As I said, this characteristic equation will have many sets of closed loop poles, depends on the value of K, infinite sets. Because as a K equal to 0, it will have one set of the closed loop poles, whereas K equal to 1, it will have another set of closed loop poles. So as K varies from 0 to infinity, there will be infinite set of closed loop poles. Each set, how many closed loop poles depends on the order of the open loop transfer function G dash of S, H of S. So here root locus gives the picture of those variation of closed loop poles as K varies from 0 to infinity. So mathematically, how to draw the root locus? So for that I will consider example. Let G of S H of S equal to K by S plus 1 into S plus 2. Now then what happens to the characteristic equation? According to the concept of the characteristic equation, 1 plus g of s h of s equal to 0. So 1 plus k into k divided by s plus 1 into s plus 2 equal to 0. So by rearranging it, s plus 1 into s plus 2 plus k equal to, that means s square plus 3s plus 2 plus k equal to 0. So this is the quadratic equation. So it will have two closed loop poles. So those closed loop poles s1 and s2 equal to, according to the algebraic concept, minus b plus or minus square root of b square minus 4ac divided by 2a. Based on that, minus 3 plus or minus square root of b square 9 minus 4 into 1 into c where it is here is 2 plus k divided by 2a. Now these closed loop poles are the functions of k. Now as I vary the k 0, and if I substitute the value of k here, I will get minus 1 and minus 2. These are the two poles when k equal to 0. When k equal to 1, if I substitute here, I will get minus 1.12, and this becomes, changes from minus 2 to minus 1.17. So as when k is equal to 0.2, this pole becomes minus 1.276, this becomes minus 1.723. So as so on. So when 0.25, if you observe, this is also minus 1.5, this is also minus 1.5. So as I am varying this k, I will get different set of values for one pole as well as to the other poles. If I plot all these poles in a variation of all these two poles in a S-plane, then we will get a root locus, something like this. So one pole S1 at minus 1 when k equal to 0, and S2 is minus 2 when k is equal to 0. As the k varies, this is minus 2 to minus 1.887, minus 1.76, like that it is varying, and then it following this, whereas this is following this. So this is the actual mathematical procedure to find out the root locus. But this is the previous problem what we have considered. It is a simple second order system. So it is easy to find it is easy to draw the root locus, and it is easy to find the closed loop poles. But suppose the order is of 5, 6, 10, because this is the example purpose. In the real time the order may be 10, 20 and so on. So in such a case, how to draw the root locus? Now before going to the construction of the root locus, in this S-plane there are many values, right? So whether any point is a part of this locus or not, if it is the part of this locus, then for what value of the k it is the part of the root locus. Now suppose this is the point which is, that is a minus 1.5 plus j.4. This is the point on the root locus for what value of the k. So we don't know. So to find out this value of k as well as whether this point is a part of the root locus or not, to check that, what is the criteria? We will study those things first. Those conditions are angle condition and magnitude condition. So consider a closed loop system whose characteristic general form is 1 plus g of s h of s equal to 0. Now if we rewrite this equation, or from the concepts of the roots of the equation, every roots satisfies its equation. According to mathematics, each and every roots satisfies its own equation. So using those concepts, I'll just rewrite this equation as g of s h of s equal to minus 1, taking to the other side, in a complex form minus 1 plus j0. Why in a complex form? because the poles either it is the real or it is the complex. So real number also can be expressed in a complex by taking imaginary value as 0. So this g of s, h of s equal to minus 1 and minus 1 equal. So if I write this in a polar form, what will happen? It becomes 1 at an angle 180 degree. So in a polar form, this is equal to 1 at an angle of minus 180 degree. Minus 180 degree or plus 180 degree. So using this magnitude and angle means whenever a point is on the root locus, it should satisfy this angle as well as this magnitude. That is what this angle condition and magnitude condition says about. So let us see. Based on this angle condition is angle of g of s h of s equal to plus or minus 2q plus 1 into 180 degree. Means it should be odd multiple of 180 degrees. 180 degree negative real value, 540 degree negative real value, 900 degree negative real value. So if I plot here this axis, it may be 180 degree or 540 degree and so on. So it should be a magnitude of minus 1. So it should be on this axis. So the angle should be 180 plus or minus 2q plus 1 into 180 degree. So this angle condition is used to test whether a point S1 in the S-plane, any point in the S-plane, whether it is the part of the root locus or not. If it gives odd multiple of 180 degree, then it is the part of the root locus. About the magnitude condition. So here magnitude is 1. So according to the magnitude condition, magnitude of g of s h of s should be equal to 1. So this magnitude condition is used to find the value of k corresponding to the point S1 in the S-plane, which is the part of the root locus. So any point S1, it is the part of the root locus tested by angle condition. Then to find the value of k at which that S1 exists, we have to use magnitude condition. So let us see one example. Consider a system with g of s h of s equal to k by s into s plus 2 into s plus 4. This is the open loop transfer function. Check whether s equal to minus 0.75 and s is equal to minus 1 plus j4 is on the root locus. If yes, find the value of k at which these poles exist. So first I will consider this point. So angle of g of s h of s at this point, to test whether this is the part of the root locus or not, is what happens, angle of k by s into s plus 2 into s plus 4 at s is equal to minus 0.75. So substitute s is equal to minus 0.75 in this. So what I will get, k divided by minus 0.75 minus 0.75 plus 2 minus 0.75 plus 4. I will substitute the value of s in this expression. So I will get angle of k by minus 3.01046. So what happens to the angle of this? This is the negative constant. So negative real value, that means angle is 180 degree. So since the angle is 180 degree minus 180 degree, which is a odd multiple of 180 degree, s is equal to 0.75 is a part of the root locus. Now I need to find, if yes, find the value of k at which this pole exists. So to find the value of k using magnitude condition, g of s h of s at s is equal to minus 0.75 should be equal to 1. So magnitude of k by s into s plus 2 s plus 4 at s is equal to minus 0.75, that is equal to magnitude of k by substituting s value minus 0.75 plus 2 minus 0.75 plus 4. So it is k by 3 point magnitude, so this minus goes off. Magnitude means always a positive value. So k by 3.046 equal to 1. So k equal to 3.046. So h is equal to minus 0.75 is a closed loop poles of the system with g of s h of s equal to k divided by s into s plus 2 s plus 4. In this case we have not really calculated whether the closed loop poles of the system, and without calculating the closed loop poles we are checking whether it is a part of the root locus or not. Now second question, h is equal to minus 1 plus j4. So angle of g of s h of s at h is equal to minus 1 j4 plus j4 is angle of substituting this value. So I will get minus 233.13. So this is not an odd multiple of 180 degree. Since this angle is not an odd multiple of 180 degree, this point s is equal to minus 1 plus j4 is not a part of the root locus. So in this session we concentrated on only the basic concepts, disadvantages of this Ritz criteria, what is the root locus, and to test whether a point is a part of the root locus or not. Still we have not come to how to construct a root locus. So how to construct a root locus or construction rules we will study in the next session.